Today we have 3 great presentations from the CousCous project, Ruotsalainen, Leena, Järvi, and Ákos. Gosztonyi, telling about the project from 3 different perspectives or disciplines: the climate, computer sciences, and social sciences. We will record this session today and then add it to our website for 2 weeks, so then also people who weren't able to attend today will be able to see it afterwards. I think we will start with Ruotsalainen's presentation. So please, Laura, I can already share the screen for you, so then you're ready to start. And if Eetu can, for example, put your thumbs up if everything looks all right. Okay, perfect.
Okay, so yes, good morning. So as I said, my name is Laura Ruotsalainen, and I'm an associate professor at the Department of Computer Science. And as said, so we are not talking about 3 different perspectives on the topic, but we are actually talking about 3 perspectives that we will be joining in the CousCous project. And I will start with the topic with artificial intelligence for sustainable urban development, and I will go through how we will then combine the results from the 3 different projects, and then after me, Leena and Ákos will talk about their own angles for the topic. But before going to today's topic, I wanted to say a few words about my own research group. So we work, as I said, at the Department of Computer Science at the university, and my research group is called Spatial Temporal Data Analysis for Sustainability Science. And in our case, it means that we are developing mainly machine learning, so many deep learning methods using spatial temporal data. And in our case, that means mainly kind of like navigation data, so position-related data. And then also developing the machine learning means then for using the data and developing means for, especially for addressing and developing autonomous systems, autonomous mobility, and that way also sustainable smart cities. And then we are also a member of and a very active member of the Finnish Center for Artificial Intelligence, so this EFCA, and I will say a few words about that work also at the end of the presentation. But okay, so before we will go to that project, I wanted to also say a few words about how the artificial intelligence will really affect the sustainability goals achievement. And there has been a very interesting research published 2 years ago about what is then the real effect of artificial intelligence, and we are trying to achieve the sustainable development goals. And the research was published in Nature Communications, and they did a very deep analysis of when we are looking at the 17 sustainable development goals, and they can be divided into 169 different targets. So when we really look in deep and analyze how do the different artificial intelligence methods and use of artificial intelligence really affect these different targets, it was found that 134 of the targets was enabled by using artificial intelligence. And of course, there is the side effect too, so 59 of those were inhibited by the use of artificial intelligence. So kind of like the strength of artificial intelligence for achieving these sustainable development goals is, of course, that we are, for example, able to model how the world behaves. So what different decisions that we make, different developments, how do they then affect the world, the system, without intervening the real actions of the world. And then, of course, kind of like there are many things that we can do, for example, monitoring how the land use changes by using, for example, satellite images, and then get some benefits from that. But then, of course, the side effect is that, for example, when developing and training the artificial intelligence methods, we use a lot of energy, which we can, of course, understand that that's then inhibiting the achievement of the goals. But quite interesting also was that the kind of highest positive impact on the different sustainable development goals was especially on the climate SDGs when we use artificial intelligence. And then, of course, the kind of like the need that our CousCous project is also addressing is that we really need some sustainability transformations. So we need big systemic changes. So our CousCous project, so with long name, Sustainable Urban Development Emerging from the Merger of Cutting-Edge Climate, Social and Computer Sciences. So CousCous is addressing now how the traffic should be developed so that we can also get sustainable smart cities for the future. And then, so as I said, the CousCous is a project that will be kind of like gathering the research of 3 research groups. So myself, looking at the computer science development for the project, then Sanna Alamantila's group, and here Ákos is presenting their work on the socio-economic side, and then Leena Järvi's group addressing the air quality topic. And then so what we are doing in CousCous is that we are now developing artificial intelligence means to balance the kind of like the livability of the cities by looking at the socio-economic aspects and the air quality by using artificial intelligence, and also kind of like addressing how the traffic flow should be done so that all these different aspects would be balanced there. And the CousCous is an Academy of Finland funded project, and we have been so far working with that for 1.5 hours and years, and we have 1.5 years still left, not hours, years. That time goes really fast, but not that fast. Yeah, and actually the first publication has already been also published, so if you are interested to find more ideas of what we are doing. But then to be able to kind of like explain my part, I have to do a very, very short introduction to machine learning. This is not going to be very in depth, but so that you will be able to follow what I will be explaining in the future. And now that we are talking about artificial intelligence, quite often we are talking about machine learning methods. And then we can divide the machine learning into 3 different kind of like types. So we can talk about unsupervised learning, where we have data, and then the machine learning finds certain patterns out from the data. So it can, for example, group the data with respect to its features. Then we are talking about supervised learning, when we know what should be the end result with certain kind of data, and we are training a model to understand that if it sees certain type of data, what can it understand from that. And then the third class of machine learning is called reinforcement learning. And there we are kind of like having a bit more open ecosystem. We are modeling something, we are simulating some certain topics, and then learning via the computer is learning to understand what kind of actions affect what kind of phenomena, and then learn via doing in that. And then in my presentation, I will be talking about 2 different kind of like machine learning methods. So in our research, we are doing traffic modeling, as said. So we are doing really good collaboration with the city of Helsinki, and we have gotten some historical traffic data that we have been now learning and modeling, so that we would be able to do some predictions of how traffic would behave in a certain area in the future. And then for that, we use so-called deep learning method, which is a part of the supervised learning. And then we are using a method called long short-term memory, so LSTM algorithms. And the reason why we are using these algorithms is that most of the deep learning methods, they are looking at very kind of like spatial distribution of the data. And now when we are talking about traffic flow, we need to also take into account what is the temporal phenomena, what are the temporal changes of the data. And therefore we are now modeling by using the historical data what the traffic could look like in the future in a certain area. Well, then when I will go a bit deeper of what is the CousCous project about, so as said, we are now joining the research from 3 different research groups. So we are joining the research of traffic flow, of the socioeconomic situation, and the air quality. And to be able to balance these very different kind of like viewpoints, so we need something sophisticated algorithms. And for that, we are using then reinforcement learning, and I will be talking a bit more about how we are doing that. But as said, in reinforcement learning, we are defining a certain environment, and then we have so-called agents kind of like interacting in the environment and learning of what kind of like behavior is good and what kind of behavior or effects are bad, and in that way balancing the situation. Okay, so I said, so in CousCous project, we are doing simulations and research from 3 different viewpoints. So we have 3 different simulations done. In my research group, I said we are modeling how the traffic would behave in the future. So we have historical data, and we are teaching the machine learning algorithms to be able to predict and then model the data, the traffic, and predict what it would look like in the future. So in the data, we have, of course, the periodical changes of the traffic. So we have the morning rush hours, and then we have the phenomena that is affecting, for example, during summer vacations and at Christmas time, and then, of course, the normal work traffic and then weekends and so on. And of course, weather also affects a lot what the traffic is like. So for example, today it is most likely a bit more difficult to drive than in a normal, very dry and sunny day. And then, of course, if there are some incidents, there are accidents, or there are some events, then they, of course, increase the number of vehicles in the traffic. So we are doing now predictions for that. Then Leena will be talking more about air quality modeling, so looking at how the buildings affect and how the air flows, or Leena will tell you the correct terms here, and how does the vegetation affect, and then, for example, how does the weather then affect the air quality. And then Ákos will be talking about the population modeling. So how is the demographics at the city area? How is the built environment affecting that? And for example, what kind of mobility modes do people have in certain areas? And then when talking about then the simulation of the traffic. So as I said, we have been having really good collaboration with the city of Helsinki, and they have pointed out a certain future city boulevard area and provided us with the initial plans for the area. And then we are using then the data from a similar area to then model how would the traffic look like in the area. And of course, here we are then looking at different changes, also thinking that now if the weather was like this, and now if there were this kind of traffic, how would that affect then the traffic in the area. And for that, for example, we have been then defining the area with having certain probabilities. So where would the vehicles most likely go if they enter the area? So how many of those would be then driving through, and how would the traffic be distributed in this certain area? And as said, for this, we are using then the long short-term memory machine learning to be able to really model what kind of phenomena there is and what phenomena affects then the traffic flow, and then getting the as realistic as possible prediction of the traffic for the future. And then as said, so then when we do have all the 3 kind of like different modelings done from the different research groups, then we should be able to join all this information and be able to provide suggestions of how the city should be planned, so that we are able to get as livable city as possible, so that we would have as good traffic flow as possible, so that people could really go to their homes and go to their offices, but at the same time have good air quality, so that the environment would be livable for the city, and also have good socio-economic state at the environment. And as you can think about these, there are some quite conflicting objectives that we have. So for example, thinking that if we have very good traffic flow, so we have quite kind of like efficient transportation means, that means that most likely we have quite many vehicles, and then that's of course, for example, conflicting the air quality situation. And the same thing, if we have a very difficult access to homes, then probably this is also affecting kind of like how people want to live in the area. And of course, depending on what kind of like people live in the area, that's of course affecting what are their preferred mobility modes there. And then for this, I said, we are now developing this reinforcement learning based algorithm. So the reinforcement learning algorithm should be now able to then really learn that how should we balance these different kind of like viewpoints of the city traffic. what kind of planning decisions should we be making? And then, for example, addressing that kind of like, should we have how many lanes for vehicles, for example, should we have? What kind of like public transportation modes should we be then balancing there, and so forth? And then what kind of like effects does this have for the air? So therefore, what we are saying, we are then using something called multi-objective reinforcement learning to be able to really balance these very different viewpoints for the planning. Okay, and as said, so in this project, we are now mainly addressing the kind of like the social and economic side of the sustainability. So I said we are looking at the air quality, looking at how the cities are livable, and looking at how the traffic flows. But then also, of course, the very important point here is also that how does the kind of like the CO2 emissions, how are they kind of like balanced with respect to the traffic, or what kind of like emissions do we get based on certain traffic? And then for that, we have also fortunately been granted a project called here AI for Less Auto, where the goal is then also to find the best kind of like traffic organizations modes, and now looking at especially at the CO2 emissions levels, and then addressing the climate change. And then here in the project, so we are working together, so Leena and my research group, and then also two research groups from Aalto University. And then we are now looking at the traffic organization from 3 different levels. So we are looking at how would autonomous driving affect the CO2 emission levels, and especially how would the electrification of vehicles then affect the CO2 level emissions. And also how should, again, now the traffic be organized so that we can get kind of like the least amount of emissions produced. And then here we are looking at the traffic organization from 3 different levels. So Ville's group is looking at kind of like how should the individual vehicles behave with respect to each other, so that we can get kind of like the least emissions produced. And then Claudio's group is looking at how should we arrange a certain kind of like traffic organization. So for example, the traffic signs and the traffic lanes and so on. And my research group is looking at a certain larger city area. So how should the whole traffic ecosystem be arranged in this area so that we can get the reduced CO2 emission level there. And then Leena's group is then, of course, then doing the CO2 emission modeling and then looking at from the climate change aspect. And then just my last slide, then I also wanted to say that also kind of like with respect or in relation to our project, there are also a bit kind of like larger research kind of like ecosystems done on this topic. So at the Finnish Center of Artificial Intelligence, we are now also very strongly addressing the sustainability viewpoint. And Finnish Center for Artificial Intelligence is a huge network of the kind of like the greatest artificial intelligence researchers in the capital area, and there we are doing a lot of like artificial intelligence research, but now also then kind of like identifying and recognizing which artificial intelligence developments are the best for addressing then also the sustainable development goals. And then there we have opened so-called virtual laboratory on sustainable mobility and autonomous systems, where we are then looking at for example, the questions that how are we able then to turn these simulations into the real world cases, or something called closing the reality gap. And then also kind of like working in collaboration with the sustainability professors and kind of like finding there also the need from the sustainability viewpoint. And that was all that I was going to talk about the project and the activities related to the topic.
Thank you so much, Laura. At the same time, I will make myself also a host there so I can let people in if someone is coming. Just a second. But please, people here or then people on Zoom, if you have any questions or comments to Laura, please do please do raise your hand or then just type your question to the chat box. Yeah, Carlos Lamola Orta. Carlos, do you want to say your question out loud or shall we read it from the chat box? Please open your mic and be clear.
I can read my own question.
Great, thank you very much.
Hi.
Very interesting, thank you. I was wondering, do you have data, because I'm also using data from the traffic, from the bike traffic, and also from the pedestrians, which is a bit maybe less robust than the car traffic. So are you modeling also those types of?
Yeah. Yes, so okay, thank you for the question. So unfortunately, we don't have the actual data of the bikes and pedestrians, but we are using the proportions because we are doing different kinds of scenarios in the CousCous project. So how should the traffic be organized? And we do, of course, have the statistics of how big portion of the people kind of like in Helsinki are using the private cars and how many people are kind of like, or how big proportion is walking or using bikes. And we are using that in the simulations, but not the actual numbers, no, unfortunately, no.
Okay, thanks.
Thank you.
Good, any other questions from the audience or comments to Laura? If not, I think we're ready to continue. Thank you very much, Laura. And then next we will have Leena Järvi continuing from the kind of with the climate package of this project. But yes, Laura, please. I think everything should be. Fine here.
So good morning also from my behalf. And now we are moving to the second point that Laura was also presenting on her slides. So we go to the air quality modeling. I'm now just figuring out how to get this perfect. So I will be talking about the air quality modeling in the CousCous project, but first I will be talking a little bit about the background of in a way, how is the urban planning, or how can it actually modify the pollutant concentrations or local air quality, and also what are the methodologies that we are using in these modeling approaches. So cities are hotspots for air pollutant and also greenhouse gas emissions. But in this presentation, we will be focusing on air pollutants, even though in my group we are doing also a lot of research concerning the greenhouse gas emissions and amounts. So what comes to the air pollutant concentration variability, so they are highly variable within city networks. So in the figure in here, you can see with the yellow-orange subplot, you can see the variability of total particle number concentrations in the city of Cambridge over a few hour period. And there you can see how there are very hot spots forming, darker red areas within the street canyon network. And then, of course, there are lighter areas in those areas where you have less traffic existing. And each of, in a way, these concentration points that you can see on these maps, they are a complex combination, or they are resulting from the complex combination of local emissions, which in this case is traffic, background concentration, so how much there are pollutants at the background outside these street canyons, what are the prevailing meteorological conditions, what kind of chemical processes or aerosol processes there are, and of course also of the local morphology, or in a way the local flow field, which is affected by the buildings and the vegetation patterns within the area. All these at the scale that you are seeing here, so it is practically impossible to do these kind of simulations with traditional air quality models because they just simply cannot solve all the processes described on that I just described within this kind of street canyon network. And that's a pity, because in a way sometimes the urban planners' interest is really at that scale. So urban planners might be interested, okay, that where are the hotspots forming within this kind of urban landscape? Is that an area where we don't want to put a bus stop, or is that an area where we don't want to put a kindergarten yard, or these kind of aspects. So in some cases, planners are really interested in what is happening there at a very local scale. And then if we are in a way, so what we in a way is that we need novel methodologies in order to be simulating these very fine scale variabilities. And then if you are in a way elaborating a bit more about the urban planning perspective, so and move especially the perspective now to the Helsinki and to the interest of CousCous project. So Helsinki aims to be carbon neutral by 2035, and actually I think that this has now been modified to 2030, if I remember correctly. But anyway, and in a way, in order to meet the kind of sustainability of the city, so reducing the CO2 emissions, at the same time when meeting the needs of the growing population moving in to Helsinki region, Helsinki plans to convert some of its access roads to so-called city boulevards, so that they are not any more these multi-lane motorways, but rather they would be these more nicer visual as visualized on the top figure on this slide. However, when we are building these city boulevards, or these boulevards are built, they will of course also have other impacts, and that is of course that they will of course affect on the local air quality, and especially those people who will be moving into the area or will be accessing or will be, as was mentioned on the previous question to Laura, that what about people who are walking, or is there data about, so people are walking there, so how could it be that we are able to in a way minimize the negative effects coming from the air quality or air pollutants to these people who live or access the area. And of course the question is that how city boulevard should be planned so that the local air quality would be as optimal as possible. So in a way here we have a link again between the greenhouse gas emissions. So the aim is to reduce greenhouse gas emissions, or one of the aims is to reduce greenhouse gas emissions, and then we are ending up on actually air quality challenge, and in a way how can we optimize the city boulevard in such a way that the air quality would be as low as possible. And in a way to address these two aspects, so first of all address to the needs of the urban planners, and also answer the need of this very fine resolution modeling that the traditional air quality models cannot do, we will be using a novel modeling method to examine the question of how to improve the air quality within the boulevards. And the methodology that we are using is so-called large eddy simulation, which solves three-dimensional flow and pollutant distributions within the urban landscapes, and so that it can do this at very high spatial and temporal resolution. So we are talking of temporal resolutions of minutes, seconds, and then we are talking of spatial resolutions of 1 meter. And we are especially using the large eddy simulation model PALM, developed in the University of Hanover, and that's especially well suited for urban areas because it can of course do this very high spatial resolution. It's heavily parallelized, so it's easy to, well, not easy, but it is convenient to use on the supercomputers. It has a nesting capability, so that you can have a kind of study area of interest in a small scale with 1 meter resolution, and around that you can have like 4 meter or 10 meter resolution areas, which kind of enable appropriate flow conditions for your area of interest. And I'm talking about flow conditions because, as mentioned earlier, meteorology is something which is very important, that how actually the pollutants which are emitted on a street canyon or city boulevard, how are they actually transported away. Also, it has these different processes which are needed to really solve air quality in street canyons. So there is aerosol dynamics and there's chemistry which are enabled. So we have already had a few different studies concerning the same question. And these have now already been before the CousCous project, but I briefly want to mention them as an example. So we have studied together with the city of Helsinki and Finnish Meteorological Institute, we have studied that how on a city boulevard, the building blocks should be planned so that they would be optimal for air quality. So you can see on the left-hand side, you can see 4 different building layout plans. There are differences in the orientation, how the building blocks, long or short building block towards the boulevard. and there are also variability in the height of the buildings. And then on the right-hand side, you can see that how pollutant concentrations in these different 4 versions appear to be looking like. So we did these 4 different simulations with the 4 different, we did with 2 different meteorological cases, these 4 different scenarios, and we simulated that, how does the ground level air quality will be looking like? And we got a result that actually there can be up to 10% differences between these 4 building block scenarios. And the one where you have the short side of the building directed to the street canyon, and where you have this kind of longer, not longer, larger scale height variability in the buildings would be resulting the best air quality. So this is just visualizing that how indeed just poorly the kind of building layouts will actually affect on the local pollutant concentrations. Another example is that, what about the street vegetation? So we studied 4 different tree layouts in a city boulevard. One where there is no trees, and I would like to emphasize that that's not really an option. So that's the base run for us in a way. So that's something that we are comparing. I mean, no one wants to have a street canyon without any trees, because that would be looking not very pretty, I would say. And of course, trees have also other benefits than just affecting the, well, not just, but than affecting the air quality. But then we had these other scenarios where the amount of trees is varying in the street canyon, and then also how does the height, different size of trees affect. And here you can see overview of the results. So again, we were studying 2 different flow conditions. So when wind is parallel to the street canyon, and when is it perpendicular to the street canyon. But what we can see is that the trees, they make the air quality worse, because what they are doing, they are blocking the kind of natural ventilation of the street canyon and create enhanced pollutant concentrations at the ground level. On the other hand, using these kind of different scenarios, we can see differences in them. And what was in our case, the kind of winning case was that there would be 3 rows of trees, so that in the middle, there would be taller trees, and then on the sides, there would be smaller trees. So these are in a way 2 examples which are kind of indicating that how these are all urban planning decisions, how the buildings are made, how the trees are made, so we can really affect that how actually the pollutant concentrations in a street canyon or in a city boulevard appear to be. In this CousCous project, what we are doing, as Laura already mentioned, so we are next going to be simulating what about different traffic scenarios. So how the traffic should be planned so that they would be creating this optimal pollutant concentrations. And with the inclusion of the socio-economic impacts that will be discussed also later today. And as already mentioned by Laura, the traffic scenarios that we will be using in our simulations will be coming from the machine learning methods. So at the end, what we are going to be doing is that we will be developing similar maps as you have been seeing before with the different traffic scenarios, and then we can really see that what are the optimal choices. And also what we will be also be doing is that our model simulation will be feeding in back to Laura's simulations, or the group of Laura who are working with these, so their simulations that have kind of which to aid in the decision making, that what kind of choices the vehicles should be making within the street network. And that was it. If you have any questions, I'm happy to take. You are freely asked them, please.
Yes, I think this is highly relevant to the urban planners in the cities, and I really hope that this material will get to all of them, and I really hope that me and Anniina can help with that as well. So do we have any questions? Anniina here, yes?
Yeah, so you have analyzed the urban boulevards, and one of the results was that the buildings with different heights and maybe also trees with different heights would be like optimal for that case. But are those results sort of applicable in other streets as well in general, or do you always need to analyze every single street by street? Yeah.
I would say that both of these are general. I mean, actually, it's not new results that the trees are making air quality worse, because it has been published, I remember already years ago in Barcelona, where you can imagine when you are walking on the streets, you have these big canopies covering in a way the street, so it's clear that in a way the pollutants are not emitting. And also I would be saying that also this variability is kind of, I mean, of course, we don't know exactly what kind of air pollutant concentrations would be appearing in different cities, but I would say that they are generalized for also other boulevard. Okay, now I'm talking about wide boulevards, so not of course narrow streets or something like that. So now we are only talking about these boulevard type roads.
Then I think Carlos has a question. Please, Carlos.
Thanks, Leena, and sorry for asking twice, but it's such a dear topic to me. So the idea with the boulevards, I think the key idea was to reduce traffic, I mean, car lanes, right? So the motorways are only for cars and they become multimodal corridors. So when you say we study how traffic should be planned on the boulevards, do you mean precisely this, the how much space for what types of modes of transportation, or what do you have in mind?
I guess Laura would be the best one, of course, to answer to this one, but what I can say that we are looking the whole picture. So also in a way, the kind of organization of the traffic light systems, all the way going from these very minimal things, and also in a way, what time of day, in a way, there should be a certain type of traffic, for example, passing the area, or should they be going the side roads or the main road or something like that. But of course, Laura would be the best person to answer to this question.
Do you want to add something, Laura?
No, I think that was fine. Yeah. Yeah.
Okay, yeah, great, super, thanks, super interesting.
Yeah, Ákos.
May I ask what is the resolution of the air quality data that you use?
A spatial resolution is 1 meter. So what you saw there are these kind of pollutant hotspots that you saw, or the kind of concentration variability. So there was a kind of one concentration value for 1 meter resolution. And if I can elaborate, so we need to go to this super fine resolution because that's when we can actually solve the flow field within street canyons. So if you would be using like 5 meter resolution and we have, for example, 20 meters with wide road, we would not be able to solve in a way how the pollutants are transported or dispersed. So that's the challenge, and that's in a way why we need to go to 1 meter resolution if we want to study these things.
Good. Thank you so much, Leena.
Thank you.
And then we will go to the final presentation by Ákos. So please, you can come to the stage, and I think, yes, your presentation will be already there. Yes, please.
Hi, thanks. I'm sorry about the small font size. I always forget that I should set it like larger because in the office we have a screen. So sorry about that. Yeah, hi, I'm Ákos, Gosztonyi, and I also work within the CousCous project under the supervision of Sanna Alamantla. And we work within the Sustainable Urban Systems Research Group. And yeah, our task within the CousCous project is to link all of these things to societal or socioeconomic questions, which is actually a sort of challenge sometimes, because like, I mean, there are, like, how would I say, for example, that's one reason why I asked about the resolution of data, because if we want to link, for example, socioeconomic aspects of the population, then we cannot go to under a certain level of resolution because of privacy issues. So that is one challenge within the data. Also, it's a pretty high opportunity that, or a big opportunity that we actually have fine resolution socioeconomic data as well, but we can only communicate it about in an aggregated level. yeah, and for us, it's also a challenge to kind of use these sorts of high resolution air pollution and air quality data too, because we have to kind of like link it to the already existing and created socioeconomic data sets, which are usually higher, like lower resolution and higher spatial coverage as well. So it takes a little bit of extra work to work on environment related socioeconomic questions, such as environmental inequalities in an urban context, which is my topic. The reason why we deal with this section within the CousCous project is that there are like large gaps within the knowledge. For example, we don't really know anything about, well, some things about air pollution related environmental inequalities within Helsinki metropolitan area. If I remember correctly, the last research on this specific topic in Helsinki was conducted in 2001. So that's been a while ago. And that was a master's thesis as well in 2016, if I remember correctly. So we need information about it, especially if you want to feed in the information into the model, to the reinforcement model that we had discussed previously. Yeah, there are other challenges as well, which I listed here, but I guess we can skip this part. And I was also asked about what specific topics we are working on at the moment. And I seriously cannot read it on this screen. So essentially, what is the relationship between income and air pollution in Helsinki metropolitan area? And how does this relationship translate into the spatial distribution of income groups and the spatial distribution of air pollution? In which locations people are the most prone to experience environmental inequality? So the first question is essentially about starting at the very beginning, because of course there are a lot of socioeconomic aspects that we could investigate, but this is the basis for most of the research that we are still missing in Helsinki metropolitan area. And building on that, because it's like a low-hanging fruit, we can also calculate certain types of environmental inequality indicators, and I have been working on one which I am going to present soon. But before that, I'm gonna discuss the data which I'm working with, some of the methods which I have been or we have been applied in our research, and some partial research, because I'm really not done with this first paper which I'm going to talk about, but I guess there are some interesting insights that might be interesting for you as well, and hopefully will be a useful input as well to the CousCous project. So the main data that I'm working on is the FMI Mfuser air quality data set. We have data starting from 2017 up until, let's say, yesterday, I guess, and it's like an hourly data, almost covering the entirety of Helsinki metropolitan area, not entirely, which is a little bit annoying. Yet again, talking about the kind of like combinability of the data sets that we are working with. So there has been some issues with aggregation, and of course, the aggregation question is also quite interesting because, as I mentioned in the beginning, I'm working on gridded socioeconomic data as well, which is which has a resolution of 250 times 250 meters. So this FMI Mfuser data set has to be kind of aggregated to that level, not only temporarily in order to kind of like make sense of the data, to be able to interpret it in terms of, you know, socioeconomic aspects, but also spatially, which is a challenge, or which has been a challenge. I'm not gonna talk about the rest of this, but we are essentially focusing on the relationship between income and air pollution or air quality. And in the end, I'm going to talk about the environmental inequality indices, which we have calculated. Yep, some methods. There's essentially two main parts of the work which we are working on right now. One is investigating income as a continuous variable in relation to the spatial distribution of air pollution. And the second one is an environmental dissimilarity analysis, which uses count data. So essentially divides the population into income groups and counts the number of people or number of households living in one grid and comparing that to the environmental aspect, which is air pollution at the moment, or PM 2.5 to be more precise. And we are also using AQI values. So let's go through some of the interesting, really preliminary findings. So there are going to be some challenges that I'm going to discuss further. But yeah, maybe a little bit of a background information about what is this environmental dissimilarity. It's a lot of text. I'm sorry about it. It seemed really okay on the big screen, but it's essentially comparing the distribution of the population to the distribution of environmental variable, in this case PM 2.5 and AQI values. AQI is air quality index. I'm sorry, I forgot to explain that. And based on this comparison, we can calculate an environmental dissimilarity index and an environmental dissimilarity gap index, which is the difference between the value calculated for one population group and the rest of the population. So you can imagine that, like, you calculate an index for low-income households or people belonging to a low-income income category, and then you calculate it for the rest of the population, and then you essentially divide the two things, and then you have a gap, which is an indicator of how dissimilarly people are experiencing either good air quality or experiencing negative, bad air quality. So you can use it both ways. And this method can also be used for identifying hotspots, actually, in terms of selecting those grids on a map which has the highest probability to have an effect on these values. Therefore, you can kind of like focus policies on those areas if you want to improve either air quality or socioeconomic status, which is, of course, like interlinked in this methodology. Absolutely small. I'm so sorry. So after the data exploration on the socioeconomic and air quality indicators, we have faced a couple of challenges. For example, like those classical social science methods, which I am familiar with, are usually failing because they don't really meet those kind of like basic assumptions of regressions that should be met in most of the cases. So that's why we tested Spearman's rank correlation on median income per capita and AQI, and PM 2.5 as well, because it doesn't require normal distribution to interpret it. And it seems like there should be some sort of correlation between income and air quality values. However, it's not that high, actually. It's like 0.24, 25, I guess, or it's not a minus, I guess, which indicates a relationship that is, the richer you are, essentially, the better air quality you have. But let's see, what if we plot it? So in these two graphs, you can see two plots. Each plot contains two splines. Essentially, one spline, the linear one, is the linear regression, and the nonlinear one is the like the fitted spline of the relationship between AQI and PM 2.5 and income. So it seems like the linear line doesn't really fit the regression. So this is actually a pretty surprising finding for me, because most of the literature describes a linear relationship between income and air quality and air pollution. However, in Helsinki metropolitan area, it seems like it's not the case. But of course, you cannot really say anything about it based on these two simple plots. So we have decided to investigate further. As you can see, the data is also pretty dispersed in terms of what is there. And of course, there are like outliers, but those outliers were kind of advised against to be removed, because those are actually not mistakes in the data collection. But I will have to argue with that because of modeling purposes. So yeah, well, our idea essentially was that it is an inverted U-shape. So there, the higher the income you have until you reach middle income, the worse air pollution you have. And then the relationship changes, turns downwards. So we decided to test this relationship with novel methodology. Of course, yet again, you can see the data is really not that well behaving, I would say, for regressions, but this methodology should be, at least to some extent, interpreted in a way that the U-shape or the inverted U-shape is proved actually based on log median income and average PM 2.5 and AQI values. It's I guess I don't have that much time to explain that in detail, because I really want to tell more about it. So the other direction that we have turned is to test it on a GAM. It's a question. It's a generalized additive model, which can be really well adjusted. And of course, it's based on only one variable, in this case, PM 2.5 and AQI explained by income. So the model R square is not actually that high. In this case, I think maybe 10%, but the residual checks actually meet here. So it seems like our finding will be approved. And it's almost, well, yeah, it is similar in case of AQI as well. So the other thing which is indicated by the residuals is that there should be quite a lot of omitted variables as well. So it's going to be super exciting to build further the model, but at this stage we are just curious about income against air quality, because there obviously is spatial autocorrelation which must be accounted for, and the variable of proximity to roads will be a very high explanatory thing, which might actually diminish this this finding, but let's see. Okay, so I have mentioned spatial autocorrelation, so we have tested that, and it turns out that both our explanatory variables and our dependent variable are highly spatially autocorrelated, which violates the basic assumption of well, almost any kind of regression model. So it's going to be a challenge, but we have some strategies that we're going to do. So that's going to be later explained in one of our papers. But it means that the independent variables are not actually independent because they depend on the neighboring blocks values. So yeah, and maybe it's too small, but the two plots on the right side are describing PM 2.5 and AQI, and it's pretty clear that the proximity of roads will be actually a useful variable when introduced in a GAN, because maybe here you can see it on a higher scale. You can essentially see the main roads on the map, because in this case, the AQI is visualized in QGIS. That's it. It's just, I thought that it would be interesting to see. Okay, so let's go to the dissimilarity analysis, but I'm gonna try to summarize it very briefly. The values are actually showing not that high level of inequality between most of the population groups. However, usually the poor people or those people who are less well off are actually how to interpret it, well, more segregated from good air quality places. So that's what the values show, but the differences are not actually that high. And I suspect that if we adjust for spatial autocorrelation in this case as well, these values will go lower. That is actually for individual income. But if we check it for household level income, the inequality is higher. That's in the right corner because I just did it yesterday. I was curious how that looks like. And it can interpret it in a way that if not adjusted for spatial autocorrelation, then the less well-off people or people belonging to the lowest income category are 17% more segregated from good air quality places, which is actually pretty surprising if you consider household income, but it's not the case for individual level income, which is yet again a very interesting research question. Why? Yes, the dissimilarity analysis can also be used to kind of identify the hotspots which have the highest impact on these values. And these are the values, or these are the grids on the map which affect the dissimilarity indexes, so not the difference, which is actually pretty descriptive as well in a way, because most of these places have high level of student population. So that's going to be interesting to see if we should include or exclude from this paper those people, because they are really the outliers which you saw in the very beginning on the plots. So it's like really low income and high density of low income people. However, it's not necessarily a very good indication in case of students of socioeconomic status, because they are prone to social mobility. They might get familial help, etc. So yeah, that's an interesting finding. And these are the hotspots which have the highest impact on the difference. So these actually are more well-off places and driving essentially the difference between the two population groups. And of course, this sort of methodology can be used to kind of like model what would happen in a grid if, let's say, someone would build a boulevard. So yeah, I guess these were most of the things that I wanted to discuss or tell you about. I guess, I mean, for me at least, it's super exciting to find this. Also, it kind of links to some economic theories as well. I mean, the inverted U shape between income and an environmental aspect, because it reminds me of this environmental Kuznets curve, which is, I know, very well criticized and etc. But I think it's an inspiring food for thought. So yeah, and I guess that would be all what I wanted to talk about today. So thanks, and yeah.
I would have a question.
Yeah.
You already mentioned that you're somehow going to implement this to the bullet kind of measurements and discussions. Do you have some other? I'm kind of highly interested in this interdisciplinary projects, always about the dialogue and the kind of the collaboration between the different work communities or sections. Is there? Yeah, would be really interesting to hear. Is there something else, or what are your kind of plans between these three different parts for the rest of the project?
Yes, can I? Okay, so no, because I forgot to mention that we have one other colleague as well, Joanne Dunlap, and she's also working on population projection and predictions. So she's building now like I don't know how many variables econometric model. So that's going to be pretty useful for that. And it was not discussed if it will be included, but I guess, I mean, whatever is useful. So, and please. You
want to add something?
Well, I can of course add from the technical viewpoint, so kind of like we are definitely, but when we are joining all this information, we are doing kind of mathematical modeling of all these different parts. And then as said, so we are trying to then balance the best kind of like optimization situation where we're kind of like, well, we would have the best optimized kind of situation, balancing these all different aspects. So that's of course from the technical viewpoint.
Yeah, that sounds really good and really kind of practical level.
Yeah.
Like really concrete results and maybe even suggestions on the best ways of planning.
Yeah, and I also think Leena mentioned that we will have kind of like different scenarios so that we are also able to say that in this kind of like scenario, we would probably have the best kind of like balance between the different aspects.
Yeah, that sounds absolutely fantastic. You mentioned the collaboration with the city of Helsinki. Is that the only city you're collaborating with, or are there some other cities?
Well, in this project, yes.
Yeah, in this project, yes. Because of course, there kind of potential cities with Esquerrata, for example, and many other cities is really high as well. I think Carlos has raised his hand. Do you have a question or comment, Carlos?
No. Old hand, sorry. Thanks, Ákos.
Leena, please.
You mentioned you showed, so you said that in the earlier results, you have found the linear relationship between the pollutants and the income. And in Helsinki, it appears to be, this first increasing and then going down. So is this that different approaches have been used in different cities, or do you really think that Helsinki is different to the cities that you have so far has been studied?
Well, the GAM, the generalized additive model, has been applied elsewhere, but not with the same results. So some results actually showed like a plateaued relationship, so not this kind of relationship, and on worse quality data, because we have like really, but compared to the rest of the literature, like high resolution data. So and yes, regardless, in most of the cases, it's like a linear relationship, which is
but it's
described.
coarser data, so that can you do it? No, you can get in a finer scale if you say so.
Yes.
And also, where do you think that this results? Why do you think there's this peak?
Oh, that's a really good question. I've been thinking about that. One is this, this outlier effect of the students, for sure. That might drive it. So that's why I'm thinking whether I should include, or we should include, that population group into the analysis, or we should, analyze them separately, because that would actually make sense. And the other is like, I can maybe go back to the, no, it's not shared.
It is shared, I think. Oh yeah, it's not. Can you click it again?
Yeah. So, is it working? Huh? So let's say, look at this. Even if we remove those grids, which are, let's say, the far left, the relationship would probably remain an inverted U, not as pronounced, but I'm suspecting that if I remove them, it will still remain an inverted U shape, and even with a higher confidence interval, which will actually be a nice thing for most of the evaluators. Yes.
Do I interpret this correct? So does this mean that in Finland, kind of like, or in Helsinki, the people with high income live in the center of the kind of like the city? And is that kind of like, do I understand it correctly that when you have high income, you also have poor air quality?
No, it's the
okay. Sorry, then
it's the other way around. It's like
okay,
like the higher, like the y-axis is actually the higher the scale, the higher the value is, the worse the air quality is.
Sorry, the worse the air quality is, the higher. Okay. Well, yeah. Well, this is quite interesting.
Yeah.
In the peak is nothing. They are not really. I mean, they are probably quite wealthy, even though it's a logarithmic scale.
Yeah.
Or I don't know. At the peak, the maximum in the way that there is this.
Yeah.
It would be interesting to identify them, and also are they someone who would be living, for example, in this boulevard?
Yeah.
Because yeah.
I mean, it's, I guess I cannot see it, but it's like perhaps 10% is the R squared. So it doesn't really explain that much of the variance, actually, but it's better than nothing. So it has some effect. I mean, income has this kind of effect on air quality or being exposed to air pollution. Yes. So yeah, it would be really interesting to see it and introduce these sort of variables in the analysis. But for this article, I think it will be already too much.
Yeah. I'm just thinking of future.
That's actually the next project.
Okay, but yeah, it's really interesting because I kind of interpret it because of course I don't understand the air quality kind of like terminology. So I thought that it's kind of like the worse the air quality, the higher the income, but it's not that. So but isn't it so that in Europe, kind of like usually the trend is that the apartments are expensive in the center of the city, and like in US, usually the kind of like more expensive apartments are far away from the center. So kind of like wouldn't that's why I kind of like misinterpreted it.
No, it's very much like Verizon actually, according to city, and to my best understanding, in most cases, it is the way it is in Helsinki as well after the bump in this graph. So of course, it's like an initial model, so it might change because if you introduce new variables, then the effect might diminish to some extent. But like above 10%, it usually stays like it is.
Yeah, I was also thinking that could it have some sort of an effect in some cities where there aren't that many citizens living in the center anymore, or that they're more like business areas or Airbnb areas or whatever, that quite a very low, like high percentage of the different properties is used for something else than actual housing of the citizens.
Exactly. So it can also be like an interesting trade-off because apparently it costs your health to become richer, apparently, if you think about it. So I'm just putting it in a way that it will be interesting to feed it into the model that you are working on. So social mobility costs your health, essentially. That's what it says in a way, just until a certain point, and then it diminishes and goes down.
Yeah, that's highly interesting. Still, if someone from Zoom wants to ask something, please raise your hand, or we have more questions here.
Oh, that was a chat question.
There is something on the chat. Yes, Carlos, please.
I was just wondering that if maybe I would like to see in that graph, in this graph that we see now, what's the kind of like the overall recommendation for pollution, like a horizontal line. I'm just thinking like, are we all equally or kind of equally screwed? And then also a vertical line that where is that tipping point after which, if you get that reach, you are more likely to kind of like get away from pollution. To kind of like contextualize it in a bit more understandable way.
Well, in this 2 lines test, I actually identified the tipping point, but based on a different model where the relationship turns, but it's more difficult methodologically to express it in monetary terms because it's not the tipping point in terms of income, but how the model changes. So it would require a bit more computation. So, but a really good idea, and I've been also thinking about that. But the more I read about it, the more difficult it became. So.
But we have to start saying no to salary rise.
And about the household income, the reason why I only told about it in the end, household income, and so far about individual level income, is that it had a really weird distribution actually when plotted against air quality values. It had like 2 tipping points going down and going up, with really high variance in the residuals as well. So it also indicates that there should be some sort of omitted variable, which should be really important. So I'm guessing, because I checked there too where the point turns, and I'm guessing that single households or people living alone have their own distribution, but when you compare it to those people who live in a family. If you think about it, it's about median income, so it also makes sense that it kind of like goes for one population group and for the other in a different way. So if we introduce that variable in the model, then that would explain more. But yes, thanks, really good point.
If I can just one wish, it would be super cool to apply this kind of very highly detailed method to a particular case. For example, I'm thinking Hämeentie was just renovated, right? So if you could look at how a change in a particular street in Helsinki, in Hämeentie, the cars were removed and now it's only a public transport street. Does that affect pollution, and does that create gentrification maybe in the way that prices go up and low-income people move away or something like that?
Good point. Yes, it's maybe next year.
Yeah, sure.
Because it's time series data, and we have the potential for that. But just to comment on that, it took me almost 1 year to aggregate the data to annual values, because it was like, I don't know, 500 gigabytes, really slow computation on my computer. So yeah, it takes time.
Yes, thank you so much, Ákos, and thank you, Carlos, for participating so actively. I really want to thank you, everyone, joining us here today. The session has been recorded and will be 2 weeks on our website. We will share it on social media as well. I think this was highly interesting and relevant information and results to other researchers interested in these topics, but especially for the people working in the cities and actually making the plans and kind of shaping our future cities and the kind of level of air quality we will be all or either enjoying or suffering in the future. Thank you very much all, and we will see you next week's Wednesday, when we will talk about a man-induced seismicity and the seismic risk project. Gregor Hillers and Pia Backlund will be then giving presentations from their work packages. Thank you very much.
Thank you.